Okay. So we are still going to look at the same slide deck from Wednesday. And we had introduced this hierarchical model, and let me just kind of show it right here, where we are trying to explain kind of the data, which is going to have a bunch of hits and outs, but for different players. And so each player has their own theta value, their own batting average. And so the hits and the outs are generated from a Bernoulli or a binomial distribution. Okay, so the individuals, ones and zeros, are going to be Bernoulli. The sum of that line will be binomial, I guess. And then, and again, each player's value comes from a beta distribution. So each player has their own batting average theta sub s for each player. That comes from a beta distribution. The beta distribution is defined by shape parameters alpha and beta. And what we said in this hierarchical model is that we don't want to just arbitrarily select the numbers alpha and beta. Okay, in the first couple weeks of the class, we arbitrarily selected values 81 and 219. But now we want to say those values themselves are random variables. And so those are hyperparameters. We kind of reformulated alpha and beta to depend only on the letter omega, okay? So we have arbitrarily set k, and basically you can get alpha by doing omega times k, and you can get beta by doing 1 minus omega times k. There's a couple other, plus and minus constants here, but it's basically omega times k is going to be your alpha, and 1 minus omega times k is going to be your beta. And we are going to leave k a fixed value at 300, and omega we will allow to vary. Okay, and so basically omega is a random variable that's going to determine a and alpha and beta, which will determine the shape of our beta distribution. So omega itself will come from a random distribution. This and we have to arbitrarily select the hyperparameters of a omega and b omega. Okay. So we arbitrarily select k to be 300. We arbitrarily select this letter, this value, and this value. All right, and then omega is drawn from this distribution. So you'll notice the values I set, I use an equal sign. When it's drawn from the distribution, I use the tilde. So omega is drawn from the beta. Okay, once we have omega, we set alpha and beta equal to these values. Once we have that, we create a beta distribution. We draw a theta sub s, a batting average. And then once we have that, we put that into a Bernoulli, and then we draw values of y, hits or outs, zeros and ones. So that is our hierarchical model. This is kind of a diagram representing that. Here's another diagram representing these things. So we have our hyperprior distribution, which is beta. That's going to determine our omega, which will give us alpha and beta. Once we have that, that gives us a beta distribution to draw our theta values. And then once we plug those into a Bernoulli, we get the individual rows of zeros and ones for each player. Okay, so here we want to set things up using the Gibbs sampler, okay, and the Gibbs sampler is going to factor our joint distribution of everything into a bunch of individual conditional distributions. The individual conditional distributions, we can say, well, for each player, that individual sequence of hits and outs are determined only by that player's theta value, okay, that player's batting average, okay, and that player's theta batting average is determined by the shape parameters alpha and beta, okay, and so we have that for player 1, we have the same thing for player 2, okay, and then but finally we also we know that alpha and beta depend on omega, okay, but there's no probability distribution between omega and alpha and beta. Those are determined deterministically, but omega is drawn probabilistically, and that comes from its probability distribution with shape parameters A omega and B omega. Okay, so this is our conditional distribution, where we are just looking at basically one variable conditioned on other variables, and this is how we factored everything out. Okay, and our setup works well for this because of kind of the hierarchical system. Whereas if you didn't have this hierarchical system, it would be a lot harder to try to figure out these conditional distributions. Okay, so we will set up the Gibbs sampler. I think this is kind of where we left off on Wednesday, and so we will take a look at this. Okay, so if we want to. All right, so the posterior distribution that we want is a distribution over 11 variables. We have 10 players, so we have 10 different theta values, one for each player, and then we have the omega value, which determines that the shape of that prior distribution from which the theta values are drawn. Okay, and so the posterior of everything is proportional to this big product of all of these conditional distributions. But if we are looking just for the posterior distribution of this individual theta for theta 1, okay, then basically everything else with respect to theta 1, all of this is unaffected by theta 1. So we can, with respect to theta 1, can all just be a constant, treated as a constant. So we can just kind of ignore all of this when we are looking just at theta 1. Okay, so we only we just kind of ignore everything except for the ones that are relevant to theta 1. So the posterior distribution of theta 1 is going to be proportional to basically the data given theta 1, the likelihood of the data, times the prior distribution of theta given A and B. So this is basically like the original beta binomial model, right? Where we said, I have one player and this is his sequence of hits and outs. And so it basically simplifies to that when you're looking at just one individual. Okay, so, and again, if you think about the matrix, okay, so you have this, this Y matrix of, hits and outs for this player 1, okay? So this is player 1, and they have, this individual has a theta 1 value, okay? And then there's player 2, and this individual has a theta value, so on and so forth. And then you have player 3, stuff like that, okay? And with the traditional beta binomial model, you have your beta distribution, and then we would just draw kind of our theta values. And we could simplify this and just say, hey, let's just look at this first row here. Okay, and the first row is basically, what we did during, week 1 or 2. Okay, and then second row, we just do the same thing. Okay. But what we want to do now is taking into account the entire data set, taking into account everybody's different values of theta that we can get, right? Can we figure out kind of what is the overall beta distribution from which everybody's theta values are drawn? Okay, so we can't just treat everybody separately because we're going to say all of these values are coming from some distribution of theta values that exist for, I don't know, baseball players. So, but as far as our sampling method goes, or Gibbs sampling, we're going to just kind of reduce it down to just individual players. And so we're going to have this for each of our different players. So So we are going to generate, and so the way we do inference here is we are going to generate kind of random values for values of theta, theta 1 and theta 2 and theta 3. We're going to just generate a whole bunch of these things. And after we generate a whole bunch of these things, we will get a sense of what the distribution of theta values look like. Okay. So a little bit of notation here. We have to, because we have this big kind of matrix, we have each individual, this would be, y11. This is hit or out for player one, I guess at bat number 1. Okay, hit or out for player 1 when they set their second at bat when they go up to bat. Hit or out for the player 1, and so on and so forth. Okay. Each player could have a different number of at-bats. Okay, so some players might have, 100 at-bats, and others might have only 90 or something like that. Okay. The posterior distribution, if you think about each kind of individual player, is you take kind of your prior. So if you remember the from our beta binomial thing, you kind of, if we had shape parameters 81 and 219, and you had 5 hits and a total of 10 at-bats, you had 5 hits and basically 5 misses, and you do 81 plus 5 and you get 86. That's what this is saying. And then you would do 219 plus, the 5 misses, which is going to be n minus the sum of the y's here. Okay. And so this is what we get. Okay, so if we define k sub s as the total number of hits for the player, okay, then we can just kind of simplify this to alpha plus the number of hits and beta plus basically the number of misses, n sub s minus k sub s. Okay, so this is how we will start to set up our Gibbs sampler, okay? We're gonna just run this a whole bunch of iterations, and like any other Markov chain, sometimes there is a bit of a burn-in period. Okay, the alpha and the beta are determined deterministically based on our omega, and so I don't have a line yet as far as what value to generate for omega. Okay, but we will have a line later to generate that. Okay, and then we are going to generate values for each player. Okay, so again, basically we have a distribution. Our posterior distribution of theta is going to be a beta distribution, after we add in kind of our hits and outs that we observed. All right. So what we're going to do is basically for every player, okay, and I'm going to have kind of a big matrix, one row for each iteration, and then we're going to have a column for each player. Okay. We are going to generate a value for one random value drawn from the beta distribution, where we're using the posterior values, alpha plus the number of hits, and beta plus basically the number of misses. Okay, so and again, these alphas are right now they're determined based on the omega, but the omega itself is random. Okay, so this is what we have. We have to, in the global environment, we have to have this information of the number of hits and the number of at-bats for each player. Okay, and we're going to have basically a vector of length s. We have 10 players, so k will be like a vector of length 10. First value is going to be how many hits player 1 got. Second value will be how many hits player 2 got. Okay, n1 will be how many at-bats player 1 had, and so on and so forth. So here we're going to just generate a whole bunch of theta values and we'll analyze our theta values. Okay. So as far as the omega goes, okay, so we can do that, and that takes care of a lot of, basically all the way up to here. Okay, that takes care of all of this, all of the different theta values for, but lastly we have the omega. Okay, how do we do the omega? So you can do it kind of a little bit analytically, but we can also just use the Metropolis algorithm. So we're going to, sampling from the conditional posterior distribution for omega, not as straightforward, but we're going to use the Metropolis algorithm to kind of solve this. Okay, and again, for the Metropolis algorithm, we just need a function that's proportional to the posterior distribution of omega. Okay, and so we can say the posterior is equal to the likelihood times the prior divided by the marginal. But again, because of the Metropolis algorithm, we don't need to worry about the marginal, which is going to be a constant. And so we just need to figure out the likelihood times the prior. Okay, so this is that's the nice thing about the Metropolis algorithm, or Metropolis-Hastings algorithm. Okay, let me go ahead and give you your first view quiz answer. The letter D. D as in dog. So, the hyperprior, so we're going to have a likelihood times a prior, okay? The hyperprior, I am arbitrarily going to select arbitrary values of 3 and 7, okay? And this will just give us kind of, what could omega be? And so this is, as you kind of abstract yourself from the data, right? So when we had the beta binomial and we had to arbitrarily select values for our beta distribution, we really wanted our beta distribution to look something reasonable, okay? So we picked 81 and 219, and that gave us some shape that we liked. As you get a layer removed, okay, now we just need to determine an omega that will kind of determine what that shape, the shape of the beta distribution is going to be. That omega value, the hyperprior distribution from which omega is going to be drawn from can be a little bit more general, right? And eventually you can have something what's called an uninformative one, which would be basically a flat distribution. Any value between 0 and 1 would be equally likely. Here we'll still put in just a little bit of kind of information, but not a ton, okay? We're going to just have shape parameters 3 and 7, so that will have a mean of around 0.3, okay? But from 0 to 1, it's going to be kind of very, very wide, versus when we had, so this is beta 37 versus beta 81, 219 is something that was very narrow, right? So we're going to give it something wide. And, again, you can keep having hyperpriors or whatever if you want, and eventually you can just kind of put in something that's flat, okay? Some kind of uninformative thing. Yeah, okay. So anyway, arbitrarily I'm just picking 3 and 7, and this is going to determine the values here, all right? And so the posterior distribution, okay, omega determines the values of alpha and beta in the prior distributions. Alpha is equal to omega times k, basically, and beta is omega times 1 minus omega times k. K has been arbitrarily selected to be 300. This is kind of the joint distribution of everything, or at least it's proportional to all of this. And right now, what we have, okay, is we have a bunch. At this point, we've sampled a bunch of values for theta, okay, and what we will do is we will propose, okay, we'll do Metropolis algorithm. We will propose a value of omega, okay. So we use some arbitrary proposal function right now, and then we have to, so once you propose, then you multiply by p move, right? P move is going to be probability of the proposed location divided by the probability of the current location. And so what is the probability of the proposed location and the probability of the current location? Well, it's going to be equal to something here, okay? So, so we have to kind of work through all of this. But this even though as messy as it is, it's doable, okay? So we can get our the posterior, basically the likelihood of our data using D binom. What's the likelihood of getting that number of hits for that player if that player's theta is this, okay? And then we can get what is the likelihood of the theta value for the given alpha and betas, or the given omega. So once we have omega, we figure out alpha and beta, and then we figure out the likelihood of this particular theta value, okay? And then we will ask, what is the likelihood of the omega value that we are proposing, okay? The likelihood of the omega value that we are proposing is going to be the d beta for the beta binomial, no, not beta binomial, beta probability density for omega given our arbitrarily selected A and B values, okay? Now, this is a big product, whole bunch of small values, and so if you just used floating point numbers, you'll almost run into you'll almost certainly run into some kind of underflow error because it can only kind of keep track of 16 decimal places of precision, and so we'll be dealing with log probabilities, and that allows us to deal with really small numbers, okay? And then we just add them rather than take the product. Okay, so what does all of that look like? All right, so this is going to give us a value that is proportional to the posterior distribution, okay? So for the omega value, okay, whatever omega value we've proposed, all right, and then our k and our thetas, okay, we will figure out, okay, what is the likelihood of our data, okay? So we have this part, all of these different things. Okay, what's the likelihood of the vector of theta values, okay, the 10 different players and their theta values, okay, and then what is the likelihood of our omega value, okay? And A omegas are 3 and B omega, beta omegas are 7, 3 and 7 here. Okay, so this is going to give us something proportional here. And so this will allow us to compare. We're going to have kind of our current omega, we will have a proposed omega, and we can evaluate the likelihood of the proposed versus the likelihood of or the probability of the proposed location and the probability of our current location. So we'll use this, plug in kind of our proposed omegas in our whatever, okay? So this is just going to be my proposal function. So given a current omega value, I'm going to generate one random value from the normal distribution centered at omega, and I'm going to give it a small-ish standard deviation. So it'll go somewhere between, plus or minus basically 0.05. Now, the omega value has to be between 0 and is bounded by 0 and 1, so I want to make sure I don't, because we're using the normal distribution to propose it, technically normal distribution goes from negative infinity to positive infinity. It's very unlikely to get out there, but it's unbounded. So just in case, just in case we propose a value that's greater than 1 or less than 0, we're going to make sure it doesn't get bigger than 1 or 0 here. Okay, and so this will return whatever omega value I propose. Right? Is that okay? So we have our current omega value. We plug that in. We propose something, and then we use the Gibbs sampler here. So not the Gibbs sampler, the Metropolis algorithm here. So this part is Gibbs for each player, and then this part is Metropolis. Okay, and so this is going to all work together to give our Markov chain business here. So yes, so we already talked about doing this for the Gibbs sampler. All right, so this part is we have our current vector of theta values that are our latest row. Okay, so each row we get new set of theta values. So we're going to use our latest row right here. And then I'm going to propose a new value for omega. And I'm going to calculate the probability of the proposed location divided by the probability of the current location. Because I'm dealing with logs, when I do division, it's going to be a subtraction. Okay, so I'm going to get the log probability of the proposed minus the log probability of the current location. That's going to be my log ratio. And then I'm going to generate a random u, and then I'm going to take the log of that random u, and if the log of the random u is, more negative than this log ratio, then we will accept it, and if it's not, we'll just leave the current omega as is. Okay, so if this is the case, the omega proposed becomes our new omega, and then we will record whatever our omega value is. Okay, so if it's not accepted, then whatever omega value we had back here remains right here, right? So it's either you accept the new value and use it, or you don't accept the new value and you just reuse the current value. Okay, so this is all of the code where we've combined the Gibbs sampler along with the Metropolis algorithm to generate values, right? Is this all right? I don't know. Okay, so let's try it out. I hope this works. You test your code and you hope it works, and then sometimes it blows up. All right, so let me clear up my environment. Okay, so here, I'm going to just generate my matrix of Y. I've got 10 players. I'm going to arbitrarily determine some these players' batting averages. So this player has a batting average of 252, 275, 246, 280, 246, so on and so forth. Okay, we also have a really good player with a batting average of 321. And I'm going to say we have a different number of at-bats. Some of the players have more at-bats than others. So some have 486 at-bats and some have 493 at-bats. And then we're going to fill in this matrix, okay? So if I just kind of take a look at, we got a bunch of zeros and ones, okay? It's fine. And then I will sum basically the how many hits they have, right? So player 1 has 118 hits out of 486 at-bats. And so if I do 118 divided by 486, his observed batting average is 0.242, 0.24279. Versus the theoretic theta that we used to generate this data was 0.252. Okay, so sometimes their things don't actually align with whatever they have. Okay, so these are kind of their empirical batting averages. Okay, And here we're going to run our Gibbs and Metropolis sampler. So I'm going to run 15,000 iterations. I'm going to make a big matrix of theta values, 15,000 rows, I think. Do I not have this in here? Okay, theta is large, okay. And our omega values, we have 15,000 things. My hyperparameter is 3 and 7, arbitrarily selected 300, and I'm going to just have a arbitrary starting value of omega of 0.27, but we will allow for it to vary. Okay. Once you have an omega, you will get kind of whatever your alpha and beta should be. So right now my alpha is 81.46 and my beta is 218.54. Okay. And we have a proposal distribution for omega. So like if I propose, so right now my omega is, I don't know, 0.27. And so when I call propose on this, it's going to propose a value like 2.255 or 0.293, okay, 0.214. So this is just, when we call propose, it's going to just generate values somewhere around 0.27. And again, if I start off at 0.01, it might propose values that are less than 0. And so to prevent us from running into issues with negative values, we'll make sure there's a hard cap at 0. Okay, and likewise for 0.99, it's not going to generate anything higher than 1. Okay, and then we can calculate the log probability of all of our data, and so we can do that. Okay, all right. So this is we'll run the Gibbs sampler, and then we'll see how all of this runs. So it's done. Okay, 15,000 iterations. Computers are fast. Okay. All right. So let's take a look at all like our different omega values that we generated here. So this looks pretty wild, okay? But this is basically a bunch of different omega values that it generated, and it looks really random, okay? But this will give us kind of a distribution here, right? So I can create a histogram of the different omega values that I have, and we see it's centered something around 0.28. I don't know, does that make sense? What are my K's? This is my K's and these are my N's. What is the sum of my K? Sum of my K is that, and the sum of my N is that. What's 1429 divided by 5066? Yeah? So my observed kind of overall proportion for all of the players, their hits and all of their at-bats, their observed kind of ratio is around 0.282. So combined, everything, our omegas, look to be centered around that. I don't know, what's the summary of my omegas? Yeah, 0.2808, so pretty close. Okay. The density of this kind of looks like that. This is my summary statistics at the 2.5, 25th, 50th, 75th, and 97.5th percentile. And then my mean of the omegas is, 0.2807. Okay. We can say, all right, what about player 1? What does, so we can look at player 1's, like the theta values, okay? So the dimensions of my theta's matrix, I've got 15,000 rows, 10 columns, but I can kind of just look at, like I can make a histogram of, for the first column, right? And this would be like player 1's histogram of theta values, okay? And this is player 2's histogram of theta values. And so here, I'm going to create a little function for where I'm going to create subset thetas to the pth column, and then we'll make a histogram for that pth column, and then we will get the kind of hits and at bats and whatever, and we will kind of see how this outputs. Okay, so let me clear that out. All right, so for player 1, okay, this is player 1's. Player 1 had 118 hits, 486 at bats, and so their empirical batting average, 118 out of 486, is around 242, 243. It's batting 243. And then when we generate a bunch of random values, the mean of this player's kind of batting average is around 0.257, okay? Or 0.258. 258 would be their median batting average. And what were the actuals? Okay. The value that was used to generate was actually 252. Okay. If we look at player 2 had a little bit more success at the plate, 139 hits versus 118, 493 at bats. There, player 2's batting average was basically 282.2819. Okay, 282, and then their 50th percentile is also 282. The value used to generate was 0.275. Okay. What about player 3? Not as successful. 119 hits, 498 at bats. Their empirical batting average was 0.238. 50th percentile is around 0.255. I don't know. The value used to generate our values was 0.246. But anyway, we now have kind of posterior. We don't actually have the actual posterior distribution itself directly, okay? But we do have a sense of what that posterior distribution looks like because we've generated a big sample of around 15,000 values from what we believe to be kind of the posterior distribution. And so this is what our Gibbs sampler has generated here. Okay, so that's what we have for this kind of system of all of these different individuals here. Okay, we have other tools. Okay, so here we kind of wrote our own Gibbs sampler combined with the Metropolis algorithm, and I think it works. I mean, it does. But we also have other systems, and so there are, I don't know, additional programs that are designed to do Gibbs sampling and do them kind of efficiently and well. And so JAGS, there used to be something called bugs, WinBugs for Windows, and then bugs was like Bayesian inference using Gibbs sampling, I think, was bugs. And then I don't know, they made an open source version called OpenBugs. And then, I don't know, something happened to that. And then so they created JAGS. JAGS is just another Gibbs sampler. And then there's something else called STAN. And I think STAN is the kind of the newest one that's more popular. And I still have to kind of read through the documentation and learn how to use it. But anyway, if you wanted to use something like JAGS, you have to download this separate program, okay? And it comes from this thing. And unfortunately, when you want to download, you have to visit SourceForge, which used to be a great site, and it's still reasonable, but it's now just bombarded with ads. So you go to the downloads page, and it takes you to here, SourceForge, and then you go to JAGS to download the file, and then you download, you're going to want to get the latest version, 4.x, and you can either get for Windows, and I think the latest version is 4.3.1, or for Mac OS, you can get, I guess, 4.3.2, okay, for Mac OS. And so you just come over here and you download it, and you just have to tolerate all of the ads on SourceForge. I guess people have to earn money to pay for the servers, but anyway, that's what we have here, okay? So you have to install that. You have to install this software called R2JAGS. So JAGS is kind of a standalone piece of software, and then you can incorporate it with different software things. And so basically R2JAGS will allow R to talk to the JAGS software, send the information over, JAGS does its computation, and it sends it back to R, okay? And they have similar things, I think, for Python as well, where you give the instructions in Python, Python then sends it over to JAGS, JAGS does the computations, and then it sends it back. Okay, so anyway, that's R2JAGS. The manual for how to use JAGS and bugs are on this site. There's different sites. The original one got taken down, got replaced with some foreign gambling site. I don't know. So anyway, you can. This is it's kind of wonky. See, here are plate diagrams for all of these things, and the language is reminiscent of R, but it's not R. So you have to you kind of you just set up a new model. So anyway, to set up the model here, basically you don't actually have to write any code regarding how to do the sampling. Okay, you just have to explain how all of the variables are related to each other. Okay, so this is what the model will look like. I'm going to run out of time. So here we are explaining. So theta is, we have the data y in our kind of global environment, and we're saying those values in y are drawn from a Bernoulli distribution. So see, this is not something that exists in R. There's no d Bernoulli in R. But we say our values in y are drawn from Bernoulli distribution. The values of theta are drawn from a beta distribution. Omega is drawn from a beta distribution, okay? And then here we have the assignment operators to say these are not randomly drawn, but these are deterministically figured out. So A omega is set to be 3, B omega is set to be 7, K is set to be 300, alpha and beta are set to be omega times this and beta times this, or 1 minus omega times this, and all of that, okay? So, and this feels really weird, but you have to wrap the whole thing and you call it a function, okay? It's not a function, but this is just in order to get R to be able to send the information down to the JAGS program and JAGS to send it back. The way the package does it is it wraps it up. It says, please wrap your model specification as a, quote, function, okay? Not an actual function that's ever run in R, but this is how these two things talk to each other, okay? What we see in here is, so the creators of JAGS clearly have been influenced by R's syntax, okay? But so, we have familiar things like these for loops, but again, it is a little bit different. We don't have this character as far as randomly determining values. We have this to, when you specify y tilde x in a linear model, but this is a little bit different. This is to say that our theta values are drawn from the beta distribution, okay? Each individual theta value, so theta subset S, and we're going to iterate for 1 through the number of players, so for players basically 1 through 10, and so on and so forth, okay? And then once you have that player's theta value, theta sub s, we will generate values from the Bernoulli, okay, to create our big matrix of y. Omega comes from a beta distribution, and so on and so forth. And so anyway, let me just run it really quick. I just want you to see what it looks like. So here I have, well, I don't know. Maybe this is not exciting for you. It's kind of exciting for me. Okay. So I create my matrix of values, okay? And then this is how I've specified the model, okay, in JAGS. All right, so this is the same code from our slides. And then these are just a few other things in order to get it to kind of interface. So you have to send the data over as a list, or basically a list of names, and then you send the parameters that you want it to figure out as a list or vector of names. You give it some initial values here, and then I execute JAGS, okay? And so what this is going to do is it's going to send everything over. JAGS is a separate program. It's going to execute the separate program. So if you try to just do library R2 JAGS without installing this separate program, okay, it's going to give you an error. It's going to say, I couldn't find this separate program. But basically, this has, you see the thing running, and this is basically this other program doing its thing, and it sends its information back. And when it sends it back, we can see, all right, what kind of values did it fit? So here we have, oh, I should have kept those other values, huh? So we have the kind of the posterior, like the distribution of omega. And so if you remember, when we did the Gibbs sampler ourselves, the 50th percentile for omega was right around 0.280, and then for player one, the kind of the median of their things was 0.252. Now I'm wondering how these things compare. Okay, but anyway, this is the result of running JAGS. Okay. And then there's a couple other, like, so when you do JAGS, you get a few other kind of functions. You can kind of create a plot here, and this plot is really hard to kind of read, but basically down here you have little confidence intervals for each player, okay? The different theta values, confidence interval for the omega, okay? And I don't know, something, there's something up here, but I'm not quite sure what that is. And then you can also see the trace plots. So this is basically the different omegas. So here you have three colors here, green, blue, and red. It's like really hard to see. But it ran the Gibbs sampler 3 different times, and it's plotting kind of the trace of the Markov chain, okay? And here it is for the thetas of player 2, the thetas of player 3, so on and so forth. Okay, make it stop. Okay, so we have that. All right, we'll wrap things up there. What did I? Just one so far? Okay, I'll go ahead and give you your last two. Last two answers are E and C. E as in elephant, C as in cat. E and C. Okay, that is it for today's lecture. So we will. So have a great weekend. We'll see you. So I'll be here on Monday, and then that will be the only lecture we have next week. Okay, so no lecture Wednesdays. See you guys Monday.